Okay, so let's begin. Thank you everyone for joining us today at the Polariton Chemistry webinar series. I'm Sindhana Paneer Sivajodi and I'm a graduate student at the University of California, San Diego in the group of Professor Hoel Yuenzhao. I'm honored to host today's speaker, Professor Randall Goldsmith from the University of Wisconsin-Madison. Before we begin with the speaker's talk, I would like to share some information about the schedule and mechanics of the webinar. So as many of you might know, the Polariton Chemistry webinars take place every Wednesday at 9 a.m. Pacific time. And for each talk, you have to register at this link. Next week, we have a special event called the Postdoc Spotlight, which will feature Dr. Claudia Clement from Universidad Autónoma de Madrid and Dr. Kyu-Hyung Park from Princeton University. If you haven't already signed up, you can sign up for the Polariton Chemistry online community, which is a Facebook public group where you can post about papers, conferences, job postings, and more related to Polariton chemistry. We also post the recorded webinars on our YouTube channel. So if you ever want to watch them again, you can watch them on YouTube. Now on to the mechanics of the webinar. If you have a question during the talk or after, you can click on the raise hand button. Once you click on the button, I will interrupt the speaker and you can ask your question publicly. And you can also use the chat to start discussions with other participants and to post written questions on the Q&A. So without further delay, let me introduce today's speaker. Professor Randall Goldsmith completed his undergraduate degrees in chemistry and biology at Cornell University. He received his PhD at Northwestern University studying photo-induced electron transfer under the direction of Professors Michael Wasilewski and Professor Mark Ratner, and performed postdoctoral work at Stanford University with Professor Morner, where he became profoundly convinced that molecules deserve to be looked at one at a time. He has been a faculty member in the Department of Chemistry at the University of Wisconsin-Madison since 2011, where his research interests spans single molecule spectroscopy, micro and nanophotonics, chemical catalysis, photochemistry, and biophysics. His work has been recognized with the DARPA Young Faculty Award, NSF Career Award, Alzheimer's Association Young Faculty Award, Dreyfus Teacher Scholar Award, and Journal of Physical Chemistry Lectureship Award. With that being said, I pass the microphone and screen to Professor Randall Goldsmith.
All right, that's my cue to share screen. Sindhana, are we sharing successfully?
Yes.
Great. Okay, so thanks so much to Sindhana, to Hoel, to Wei, to the whole Polariton seminar series team. This has been the seminar series has been a bright spot in a long summer. And the seminars themselves have been fantastic. I've seen about 3/4 of them. And it's really a pleasure to be able to contribute our work to this wonderful seminar series as well. Okay, so I'm going to begin by talking about my group's motivations for getting into this business. And we really sort of stumbled into this world of polaritons. But before I do that, I'll introduce kind of the important people involved. I'll introduce first a very important collaborator, David Masiello, and his team of theorists at the University of Washington. David's been my longtime collaborator now. He has profoundly influenced the way my group does experiments, which is exactly what you want in a theory collaborator. I'll also thank the students and postdocs from my group who've contributed to this project, many of whom have now gone on to bigger and better things. And then depending on how much time we have, I'll also be talking about a second project where my collaborator is Sheila McCormick and her group at the Okinawa Institute of Technology, and then the students involved in that as well. So Eric, Fong, Morgan, Kevin, Huang, Casey, and Levi. I think at least a few of you are tuned in right now too. Thanks so much, and I look forward to talking about your work. Okay, so, and funders, of course, too. Okay, so I'm a chemist and I'm coming from a chemistry department, and my motivations are profoundly chemical. For the physicists and electrical engineers on the seminar right now, bear with me. We've got a couple slides of chemistry. Those are the most chemistry heavy slides. To motivate the work, I'm going to use this arrow. This is no normal arrow. This is a magic arrow. It's a magic arrow because it represents any chemical property that I want to study. And the great thing about molecules, right, is that they do things, they undergo dynamics. And so that arrow might represent an oxidation state of metal inside of a catalytic cycle. A different mood, that arrow might represent a conformational degree of freedom in a biological molecule, like a protein. And these types of dynamics are what I'm interested in. But there's a problem, right? You got lots of molecules in your chemical ensemble, maybe even Avogadro's number of molecules. And so when you go to make an ensemble measurement, right, all you see is a boring, unchanging average. All that rich information like chemical dynamics, or a lot of it, is hidden from you. But if you can make that measurement one molecule at a time, then all that information comes crashing back. This is why we try to make measurements on individual molecules and individual particles. And so the main focus of my group at UW-Madison is building and developing tools that allow us to watch chemistry happen, to allow us to understand the fundamentals of material science, to allow us to understand quantum phenomena in molecules, for us to understand biophysical processes. Sometimes those tools are themselves molecules. For example, synthesizing functional catalyst molecules with fluorescent labels on them that allow us to learn mechanistically interesting things about how those catalysts operate. Sometimes those tools are a microfluidic device. In this case, we have a microfluidic trap that can actually cancel Brownian motion over some time and length scales. We use this trap to look at dynamics of biological molecules involved in neurodegenerative diseases. We've recently started having a lot of fun with microdroplets, and so we're using microdroplets to contain small ensembles of molecules and even single molecules to watch chemical reaction dynamics. And a major theme of the group that I'll spend kind of the rest of the talk focusing on is using various micro and nanophotonic elements. And so one of the themes that I won't talk about is, that we've shown, is using these devices called zero-mode waveguides in conjunction with FRET to allow us to do single molecule fluorescence measurements at record high concentrations, even up to millimolar concentrations. And so it was this idea of using micro and nanophotonics to watch.
Professor, I think we're not able to hear you clearly because you're too close to the microphone.
Oh, okay.
Yeah.
Is this a little better?
Yes.
Okay, great. I'll just backtrack a second. We can use these zero-mode waveguides to do single molecule fluorescence measurements, millimolar concentrations. And it was really this notion of using micro and nanophotonic devices to watch chemistry that got us into this polaritoms business. And so the tool that we wanted to develop was a way to do spectroscopy on individual molecules that were themselves not fluorescent, or more broadly speaking, not photoluminescent. And I can kind of illustrate this here a little bit. You know, we might want to study this catalyst on the right, but we were forced to synthesize this other catalyst with this big, bulky fluorescent group attached to it. There are other times where there's information contained in spectra that you can't get by labeling. And so as an example, I put this ruthenium dimer water splitting catalyst from Tom Meyer's group. So as this catalyst cycles through various redox states, the electronic structure of the catalyst changes, and as a consequence, its electronic absorption spectrum changes. If you could measure the time-varying electronic absorption spectrum of a single working catalyst molecule, you could learn profoundly interesting mechanistic details, right? This is sort of one of our long-term goals. Okay, but the catalyst isn't fluorescent, okay? So how do you measure it? A number of groups have been very active in trying to answer this question. How do you do spectroscopy on individual molecules without fluorescence? Including the seminal work of my old boss, W.E. Murner, in measuring the absorption of molecules for the first time. That was actually a direct absorption measurement. I'm not going to go into all these different experiments. They're all very creative and they're all very powerful. I will say that, at least in terms of applications for single molecules, most of these techniques have sort of stalled out at the proof of concepts phase, right? Being able to get to sort of robust spectroscopy on individual molecules, where we can look at chemical dynamics, is still very much an outstanding challenge. And that's the space we're trying to fill. Okay, so here's how we thought about this. If I take a molecule and I pump it into some electronic excited state, if it fluoresces, great, I have easy ways of doing spectroscopy. But if it doesn't fluoresce, it's probably because that excitation is being consumed by internal conversion. And so ultimately, all of the energy is getting dissipated as heat. And if I had an absurdly sensitive thermometer, I could detect that heat, I could do photothermal spectroscopy, and then infer the initial absorption event. Okay? And so what we're going to use for that absurdly sensitive thermometer is a device called an optical microresonator, or in our case, a whispering gallery mode optical microresonator. And so I can imagine building the structure by taking a fiber optic, so a region of high end sandwiched between two regions of low end, and sort of wrapping it around itself to make this whispering gallery mode structure. Once I've made it, right, there's a very simple geometric resonance condition where an integer times the wavelength is set equal to the circumference and then multiplied by a factor of next to get the optical path length. A very simple geometric resonance condition to tell me which wavelengths are allowed inside of my resonator. I can then couple photons into this resonator by taking another fiber optic and bringing it very close. I can then evanescently couple photons into the resonator. You can then ask the question, well, how long will they stay there? All right. Well, if I make my resonator very transparent to avoid absorption losses and very smooth to avoid scattering losses, the answer is a very long time. And so a particular type of microresonator, a microtoroid, was developed by Kari Vahala's group at Caltech. These are our pictures. We fabricate these microtoroids at UW-Madison. And these are really amazing structures. You can potentially get to quality factors up to and exceeding 10 to the 8th. So very high quality factors. You can take an optical fiber and bring it very close. And if you plot the transmission through that fiber as a function of input wavelength, every so often you'll get a dip every time you satisfy that very simple geometric resonance condition. And because the quality factor of these resonators is so high, the width of these dips is very, very narrow, to the tune of a small number of tens of femtometers. Okay, they're so narrow that if you look at these things funny, okay, they shift, which means what you've made is a very responsive sensor of the microenvironment surrounding the toroid, maybe even sensitive enough to measure the heat dissipated by individual molecules. And so I'll talk a little bit more about the fundamentals of these devices. I can define a major diameter and a minor diameter, and I can use these quantities to then look at the mode structure. I need 4 mode numbers, or if you want to think about them as quantum numbers, to describe the mode that I'm looking at. The first, the azimuthal number, is the same number that I talked about a minute ago, right? That's the number that I'm using to multiply by wavelength, then equal to the circumference. But if I zoom in on the cross section, and it's a little bit hard to see, you can kind of make out the cross section of the resonator there. I need 2 other mode numbers to fully determine the nodal structure of the mode that I'm looking at. And then finally, I also, in some cases, have a splitting splitting of the degeneracy between the clockwise and counterclockwise propagating modes. You actually saw that in the previous slide when I showed you a doublet. So ultimately, I need 4 quantum numbers or 4 mode numbers to describe the mode. Okay, so these resonators are so sensitive that it's not surprising there's been a whole community that's popped up for using them for so-called label-free biosensing. And so the way these experiments generally work is I have a molecule somewhere in solution and it comes in and sticks to the resonator. It then has a refractive index that is different from whatever its solvent molecules were displaced, and I get a little shift of that resonance. And there's been kind of an arms race in this community to detect smaller and smaller objects, so single particles, single proteins, single small molecules, even single ions. Okay? But for all these measurements, all you can do is detect that something is found. How do you know what has found? Surface chemistry can get you part of the way here. But if you could do spectroscopy on each individual molecule that was being bound, you wouldn't be doing label-free detection. You'd be doing label-free chemical identification, or spectroscopic identification, which would be vastly more powerful. This is one of our sort of long-term goals. Okay, and so here's our experiment. Okay, we have our resonators. We take a fiber optic. We couple photons into the resonator. We then take an object, put it on the surface. At this point, one where we know what it is. We then come in with a second beam, a free space beam, and we drive some excitation. It could be an electronic excitation or plasmonic excitation. We drive some excitation of that molecule or particle. Okay, we don't just pump it, we pump the crap out of it. Okay, so we dissipate a whole bunch of energy, heat, which gives us a local temperature change, which changes the refractive index. Okay, we also saw this concept introduced in Saeed's excellent talk last week about the temperature-dependent refractive index. Okay, we change the refractive index, which then changes the optical path length, which then shifts the resonance. And if I can then measure that resonance shift as a function of the color of my pumping, I can directly trace out an absorption spectrum without ever having to have an emitted photon. So these resonators are platforms for doing spectroscopy. Okay, so great, we can make resonators. We were really bad at it for a long time, but we're pretty good at it now. We can then couple photons into it by taking a fiber and moving it very close to the resonator. You're seeing it from a top-down and a side-on perspective. And the good news is that it kind of works. So we started out with easy objects first, big objects, carbon nanotubes. You can take your beam, you can move it around, and then image these individual nanotubes, not by light emitted, not by light transmitted, but by heat as registered by the resonator. We can also add in simulations to be more quantitative. And so what I'm going to show you now are cross sections through the resonator. We can simulate an electric field distribution of the optical mode. We can also say if I have a little nano furnace, right, some molecule dissipating heat on the resonator, right, I can calculate a temperature profile. And then I can, as a consequence, I can then calculate a refractive index profile. And if I take an overlap integral between that refractive index profile and the mode profile, I can then say, if I'm dissipating this much energy, I know my resonance should shift by this much. Okay, and then if I also know how many photons I'm raining down from above, I can then calculate an absolute absorption cross-section. In this case, per carbon, I can then compare that with literature values for these nanotubes, and I get the same number. So you should trust me when I can say I can measure absolute absorption cross-sections. We also wanted to show in the early days that we could do spectroscopy. And so we can just change the color of our pump beam. We got ourselves some gold nanorods because we thought they'd be easy and boring. We'll later show you that they're not easy nor boring. And measured spectrum. And they're in the near IR. I'll tell you why they're in the near IR in a couple more slides. And we basically hoped we'd catch sort of the tips of Lorentzians or the red edge or the blue edge, and that indeed that is what we see. Okay, but if we want to get more sensitive, but we need to get more sensitive to get to individual molecules. And so we need to play some instrumentation tricks first, and then we'll get to the polaritons, I promise. And so in the old days of this experiment, we would take the laser and we take our probe laser and dither it in wavelength space. Okay, and then you would know, right, when your microresonator shifted because some molecule or particle was dissipating thermal energy. But it's inefficient, right? You're spending most of your time not coupled to the resonator. You'd much rather have a situation where it's coupled all the time. The probe laser is locked to the microresonator and follows it. To do this, you need to generate a signed error signal. We can do that using a technique called power-driven optic. Basically, what we do here is we take our probe beam, we phase modulate it, and then depending on the offset between that probe wavelength and the resonance of the resonator, it'll change the phase shift of that probe. And then we can measure that phase shift by mixing in a local oscillator and then reading it out as a DC signal. So great, I can now lock my laser to my resonator. And so what I'm doing here, and it's just kind of a Rube Goldberg, right, is I'm taking the absorption cross-section of my molecule or particle, I'm mapping it onto a temperature change, I'm mapping that onto a refractive index, I'm mapping that onto a resonance shift to my resonator, I'm mapping that onto a phase shift, And then good God, at the end, finally, right, I'm then extracting some kind of signal that I can read out. Okay, but to really get the benefit of this, and if you're working this hard, hopefully there's a benefit at the end, I have to add in a few more boxes. So at the same time that I'm doing this phase modulation loop, I'm also amplitude modulating my pumping. What this allows me to do is then to take that little bit of signal that I'm going to get and concentrate it into a very, very narrow frequency band. Okay, and so, you know, my signal might be fluctuating for a variety of reasons. It might be because of laser frequency jitter at very, very high frequencies, at very, very low frequencies. Maybe my students just had lunch and now the temperature in the room is rising, right? But I know that that little signal that I'm fishing out of this ocean of noise is at this very specific frequency band that I determined. And so I can use a lock-in amplifier to fish it out. And so doing this, I can actually, with this double modulation scheme, I can actually measure resonant shifts down to under 100 hertz or less than 1 attometer of wavelength shift of the resonator. Okay, so we're very, very sensitive. I can compare that to the amount of that thermal energy dissipated by a single molecule pumped in near saturation, and it's a limited detection of about 1,000 times of what I'm able to measure. We're also largely immune to scattering because it's photothermal. Background is still high, and that's what I'll talk about next. The reason that our background is high is because you can kind of see that here are the nanotubes, but you can kind of make out this sort of shadow of the resonator. That's bad news. The reason we're seeing that is because even though the ring of my toroid, the disc, is made of glass, the substrate and the post are all silicon, which is an excellent absorber of visible photons. Wouldn't it be great if we could make an all glass resonator? And so we did that. We basically made upside down toroids first, so silicon on glass instead of glass on silicon. We then oxidized silicon to glass to make this all glass structure, and then we can do a chip scale thermal reflow to make these all glass toroids that I'm showing you now. This is the old background, this is the new background, dropped by about 4 orders of magnitude. We can also do mapping, so we can map out individual objects. We can get fancy journal covers. I like showing this cover because I can get good advice to other assistant professors in the audience. So, you know, in 2016, I was an assistant professor who definitely needed the sort of peace of mind and self-validation that came with the cover. Advanced materials, like most Wiley journals, 5 covers per issue. So you're basically guaranteed a cover if you apply for one. You'll just have to pay about 2,000 euros for the privilege. Anyway, the other way to lower background is to do spectroscopy at a pump wavelength that's below the bandgap of silicon, so in the near infrared. So that's why you'll see that a lot of our measurements are in the near infrared. Okay, so we've had a lot of fun with this platform. We can use it for looking at materials, such as looking at conductive polymers. I won't talk about this story. We can also take the whole operation and put it in water to look at chemical reaction dynamics. I may have time for this story at the end, we'll see. But most of what I'm going to spend the rest of the talk talking about is looking at hybrid photonic-plasmonic structures that we get when we look at gold nanorods that are sitting on the surface of our resonator. And so I'll kind of motivate this a little bit using some of the language that's become familiar in this seminar series. If I want to think about maximizing my light-matter interaction, I want to first talk about quality factor. I can relate the quality factor to the line width of the resonances of my cavity. And here for a 10 to the 8th Q, here's a bunch of line widths, and hopefully I found your favorite units here. If your favorite units are hard trees, I'm sorry. I can also relate that quality factor to a residency time, okay, or a ring down time. And I can give a number here. And so I can think about quality factor as the ability of my cavity to localize photons in time. And indeed, for a 10 to the 8th Q resonator, you're really allowing your photons to stick around for a long time. The quantity that's gotten, I think, more attention in this seminar series, and with certain types of macroscopic resonators, you can get to amazingly high Qs, like 10 to the 11th and above. The other number I want to talk about is the mode volume, which I can think about as a reflection of the ability to localize light in space. The mode volumes for these microtoroids, this was alluded to in Javier's talk as well, is sort of middling. They're really microstructures, not nanostructures. And I'll talk a bit more about this later, in the talk. So if I want to maximize my light matter interaction, I'm looking to maximize this ratio. Okay, so how do I do that? Okay, is there money on the table in terms of getting a higher quality factor? So I can break up my total quality factor into a sum of the reciprocals of my individual quality factors. I have my materials absorption, which I can put again in your favorite unit depending on what community you're coming from, an extinction coefficient, complex element of the refractive index. I can think about scattering losses. This will be easier to minimize for larger resonators because it's easier to make bigger things than smaller things. And I can have my radiative losses. I can make my life easier here by having larger refractive index contrast, or again, making my resonator larger. As I do both of these things, my radiative losses will go down and my Q-rad value will go up. Okay, so how do I maximize this quantity, right? If I have, for example, high refractive index contrast, I can make really, really small resonators, like these silicon carbide microdiscs. Okay, so I can make my resonators larger, right? This will minimize radiative losses. It'll also minimize scattering losses, okay? But I've also made a larger resonator. So mode volume goes up. So I haven't maybe gained very much, okay? I could also think about just increasing the refractive index contrast, okay? Then I can make smaller resonators, okay? But because of the Kramers-Kronig relations linking the real and imaginary parts of my refractive index, it's hard to make the real part big without also making the complex part big. And so it's hard to push there either. Hard to push there as well. So can I think about other cavity designs? And so I'm particularly excited about these, not so much new, but rapidly improving photonic crystal cavities and so-called nanobeams. Here I'm showing a picture from Marco Lanchar's work. One can potentially get to higher Q over V's in dielectric cavities using structures such as these. We wanted to come at this at a different way. And I say we want to come at it, this is a little bit, kind of chronologically incorrect. Like I said before, we stumbled into it, but I'm also ultimately going to bring it back to this idea of making a larger light matter interaction. Okay, so I come back to this slide. Okay, we put these gold nanorods onto our microtoroids. We did spectroscopy, and we really wanted a boring result. That's why we picked those gold nanorods. And if you scan in wavelength, okay, very quickly, your pump wavelength, right? You just get these Lorentzians. You get the boring result that we hope to see. But if you scan much more slowly, if you in effect do high resolution spectroscopy, okay, you get a whole forest of peaks, right? And some go down, some go up and then down, some go down and up. You get these beautiful and very, very sharp, so these are micro EV features, these very, very sharp Fano resonances. We shouldn't have been surprised to see this. Other groups have seen similar line shapes like this. And here I'm just giving two examples on the left from Lehman Tong's group, on the right from Oscar Peña's group, of putting various nano objects on whispering gallery mode dielectric resonators. And you also see these Fano line shapes. The difference here is that in these experiments, you were seeing the line shapes in emission. Because we're able to do absorption spectroscopy, photothermal absorption spectroscopy, we can actually see the signatures of the interactions between our plasmonic system and our photonic system, even in the absorption feature. And that's powerful, and I'll talk about that's powerful in a little bit. Okay, so great. So what are the ingredients that you need to have a Fano resonance? Okay, so I need a broad feature, in this case provided by my surface plasmon. And I also need a bunch of narrow features, in this case provided by my whispering gallery modes. Now, in the atomic resonances that Fano was studying, okay, your free space beam could drive transitions into both of these manifolds. That's not true for our system. So Abe Nitzan once told me that I should be calling this a Fano-like system, and Abe's a lot smarter than I am, so I like to generally listen to what he says, listen to what he tells me to do. And so in this Fano-like system, my free space beam can't drive transitions in the whispering gallery modes, but the whispering gallery modes are coupled to my plasmon and can exert a back action upon that plasmon and then interfere with that driving frequency. And then if interference is important, then obviously phase is very important. And so what I'm plotting here is the phase shift of my whispering gallery modes on top and my localized surface plasmon on the bottom as I take my driving beam and I tune through those resonances. I get a phase shift, right? But I get a different phase shift. And so if I zoom in on this left one first, where the whispering gallery mode is redshifted relative to the center frequency of the localized surface plasmon. Okay, you can see that on one side, right, my phase shifts are relatively small, and so I expect constructive interference. And then on the other side, I get a big phase shift really quickly, and so I get destructive interference. And so I'm not surprised to see kind of a constructive gain on one side, and then a destructive loss on the other side. Now, the opposite is true when I go on the blue side of that localized surface plasmon, except it's flipped now, right? And then for a resonance right in the middle, right, I'm basically destructive all the way through because they both flip. And so I see only destructive interference and a drop in my signal intensity. And again, and that's what I see in the data. We'll be a bit more quantitative about this in a second. Okay, so I can quantify the shape of that resonance as I tune it across the whispering gallery mode by this factor little q, uncreatively called the Fano asymmetry parameter. But I can take every single one of these resonances and extract that little q. And sure enough, it goes up and down on one side, down in the middle, down and then up on the other side. I can fit every single one of these to this Fano logic equation, extract little q, and plot it as a function of energy, and I get a line. Okay, so great, there's my line. Okay, I come back to the theory. We'll talk more about this in a couple more slides and say what that dependence should be, and it should be a line, at least in some regimes. Okay, and it should be a line whose position and slope is only a function of two other experimental parameters, the plasmon center frequency and line width, both of which I can measure independently. And I do that, and I get the same line. I think this is super cool for a bunch of reasons. One, I love the idea that we can take this horribly nonlinear thing and get something linear. That's just really satisfying to me. We can also do these measurements in absorption on these non-emissive objects. And then because we have this dense forest of whispering gallery modes, because of the mode structure I introduced before, we can map out this whole dependence for a single object. I think that's really satisfying. It also makes for additional predictions, right? If I have multiple nanorods all on the same whispering gallery mode resonator, then they should all be talking to the same whispering gallery modes, which means their resonances should be in more or less the same position. And they are, okay? But because the plasmons themselves, right, might have different center frequencies because of fabrication defects, the detuning will be a little bit different. And so I expect the shapes of these resonances to also be different, right, but in the same spectral locations, and that's what I see. If I look at resonances on a different resonator, I just see only accidental overlap. And if I look at nanorods that aren't sitting at the edge of the resonator, they're a little bit farther back, so they don't have good overlap with the whispering gallery modes, then I never see any of this. And so it all kind of makes sense. And when you start thinking that your science is making sense, it's a good time to start challenging that science. And so we challenged ourselves to then start thinking about, could we actually control the shape of these resonances? And to do that, it seems like all I have to do is change the detuning between my localized surface plasmon and my whispering gallery modes. One way of doing that would be to just change the whispering gallery modes. We actually published a way of doing this photothermally, but then we'd be doing everything photothermally, and that seemed kind of complicated. And so instead, we said, well, can we just change the LSP energy? Can we change that frequency? And to do that, all we have to do is change the aspect ratio of the nanorod, just by a little bit, right? Basically just kind of soften the edges. We figured, okay, we're already doing a photothermal measurement. Let's just crank up the intensity of our laser, okay? And then maybe I can kind of controllably melt the nanorod. And this looked like it would work, but nothing happened, but then poof, everything would happen, okay? And so it was sort of like, you know, using a sledgehammer when you should have been using a scalpel. And so my student Kevin was getting really frustrated, right? He thought he was close, but he kept melting his nanorods. And I thought we were close. And so, you know, at this point, I feel like a really, you know, wise advisor will offer that, you know, kind of nugget of wisdom to advance the project. And all I can say is that, you know, I kind of did the best that I could under these circumstances. You know, just keep trying. And so Kevin was sort of the perfect kind of graduate student. He told me what I needed to hear. But then he went into lab and came up with a much more clever idea. And so what Kevin found in the literature was that the melting of nanorods, gold nanorods, is actually a self-limiting process. And so if you heat that nanorod at 130 degrees for 5 minutes or 5 hours, you get the same nanorod. But if you heat it up to 132 degrees, okay, you get a different nanorod. And so we come up with this scheme of alternating between heating cycles, where we just put the whole chip on a hot plate, and spectroscopy cycles. And then the sort of PowerPoint version is we'd hope to kind of march the spectrum of the nanorod kind of across the visible spectrum, across our visible spectrum. That's PowerPoint version. Here's data, right? So great, we can do that. We can actually move the resonance around. And then at the same time, here's back to the PowerPoint version. Sitting at one spectral position, we hope to be able to change that final line shape. And here's data. At first, nothing happens, but you keep doing it because you're a stubborn experimentalist. Eventually, you can make it through the whole menagerie of shapes. Here's one final resonance. Here's another on the same toroid. Here's another on the same toroid. Remember, we had this complicated mode structure, so we have lots of resonances to look at. And it's great. We can see it, right? We can go through this whole menagerie of shapes. It's kind of what we expected. It doesn't happen very often in science, so we should be, kind of savor that feeling. But on the other hand, we saw something we didn't expect. We saw this envelope, okay? That's really interesting. It's also sort of unfortunate because the line shape equation we were using basically forces the resonances to go to 0, which means we were suddenly getting really bad fits, okay? So we went back to David's group and we said, David, we broke your theory. We need a new theory. And so I'll quickly introduce the original theory and then talk about how we modified it. And so the equations of motion I'm showing here are parametrized in terms of the generalized momentum. You can think of that as a number that's just proportional to the electric field. On top, I have the equations of motion for my plasmon. It has some resonance frequency. It's driven. It also has some loss on it because plasmons are lossy. And then on the bottom, I have the equation of motion for my whispering gallery mode. It has its own resonance frequency, but it is not being driven directly. And then I coupled the two. And if I solve these equations of motion, then I can write an equation down for my Fano symmetry parameter in terms of some kind of more complicated derived quantities. And then I can take kind of a limit and get to this linear form that I showed you before. But again, this resulted in lousy fits. So we said, okay, well, how can we change that? So before, we didn't have any dampening terms for our whispering gallery modes. That felt like a pretty good approximation, right? Because the quality factors were something like 10 to the 7th, okay, as compared to the plasmon, which had a quality factor of about 20, okay? And so by not having that term here, we were basically assuming a quality factor of infinity, okay? So we just added in a dampening term. And then when you resolve these equations of motion, right, for that Fano symmetry parameter, it becomes complex. Okay, so you pick up this imaginary term. And now when we go to actually fit our resonances, right, here was our old fit, here's our new fit. We can actually capture this behavior that we're seeing, at least for one Fano resonance. Okay, let's now plug it in and see if we can actually use this to capture the behavior that we see. We're going to take that middle one there. We're going to use 5 parameters to fit it, okay? So 2 center frequencies, 2 line widths, and a coupling parameter. Okay, I can actually measure my plasmon center frequency independently, so it's only 4 free parameters. And once I have these 5 parameters, I can then plug them into this equation and extract out the real part and the imaginary part of that complex Fano symmetry parameter. Okay, then I can say, well, that's just for this first one here in the middle, right? I can then kind of propagate backwards and forwards in time to my kind of unmelted and to be melted nanorods and predict what the real and imaginary parts should be. And I get a line there, I get a curve there. Okay, it's also an experiment, so I have some measurement uncertainty, so I'll give myself some confidence intervals as well. I can then go back and measure these parameters for every single one of these individual Fano resonances. And I can use that to fill in these graphics here, okay? And I find it great. I can actually capture the behavior that I'm seeing. I want to deconstruct this just a little bit more. So ultimately, I'm seeing these Fano resonances because of an interference phenomenon. And so phase is important, right? What if your phase is getting messed up? And so in my original line shape equation, my Fano resonance was going all the way to 0. I was basically getting perfect destructive interference. And so if I'm not getting that, right, it's because somehow I've messed up those phase relationships that got me there. And so I can borrow some concepts from the magnetic resonance literature to kind of deconstruct those dephasing, that dephasing. I can define a total dephasing, a T2 time, and I can define it as a sum of the reciprocals of a T1 time that I can tie to relaxation, something that is connected to the dampening parameters that I showed you before, and a pure dephasing time that comes from random fluctuations of energy levels. In the mesoscopic conduction literature, which is one of the other places you find complex Fano resonances, it's a T2 star process. So you can take this and cool it down to very, very low temperatures, and the perfect destructive interference returns. For us, at least in our theoretical treatment, the dephasing is coming from that relaxation process. And so we've been thinking about this as a T1 dominated process. Okay. Okay, so why does any of this matter? Okay, so we're coupling our plasmonic system to our photonic system, our dielectric cavity. Our dielectric cavity, our whispering diode cavity, gives us a super high quality factor, but kind of a middling mode volume. Okay, whereas our nanorod has a lousy Q, but it has a nanoscopic mode volume, or if I can, kind of reinvent a term used by Javier and Jeremy, maybe even a picoscopic mode volume. Okay, but maybe by combining these, by hybridizing these systems, I can mix them in a way that maximizes Q and minimizes V. And if I can do that, I can get to stronger coupling. Maybe I even can get to other emergent physics as well. And so these are the numbers that I have. It's hard to calculate them, but I have a way of actually measuring them from the spectrum that I acquire. So I can get them experimentally. And if I'm thinking about more fully describing the system, oh, sorry, got ahead of myself. And so with these values that I extract experimentally, I can calculate a Purcell factor, which is proportional to Q over V. And I can compare, the hybridized system, right, to just having the system being very, very detuned from each other. And what do I see? I see over an order of magnitude, about an order of magnitude increasing Q over V. So I'm seeing advantages in terms of getting stronger light matter interactions by hybridizing these two systems. Okay, are there other things that I can learn? Okay, so I can measure my resonance frequency. I can measure the coupling. Most of what I've talked about is focused on the non-radiative rates. Okay, but I also have these radiative terms. Okay, and my resonator is also going to have a radiative term as well as non-radiative term. I also have a loss term coupling to my fiber. And if I want to completely describe my system, I want to be able to quantify all of these terms. Okay, but if I want to extract more information, I need to add more measurements as well. Okay, and so in addition to our photothermal measurement, we're also measuring what we call the two-sided scattering spectrum. And so the idea is that even as a lot of this pumping is being absorbed, some of it is elastically scattered into the resonator, and some of those photons are then coupled into the fiber. Okay, and if I can measure those photons, maybe I can extract additional information about my system. And so to do that, we basically added in a second lock-in amplifier to our system because, why have one lock-in amplifier? We can have two lock-in amplifiers. And we still have our photothermal measurement. So we use a wavelength division multiplexer to filter out just the probe beam. So it's something that's detuned from our pumping. But then we can also harvest our elastically scattered photons and send them to a different lock-in amplifier. And by doing that, sorry, I'm just moving my cursor around. By doing that, I can measure my absorption spectrum as well as this two-sided transmission spectrum, sort of a kind of a derived scattering spectrum. I can fit both those quantities simultaneously and extract all of the quantities that I showed you before in that picture. I think this is really cool because if you put all these quantities on the same plot, right, they span something like 9 orders of magnitude. It's really a remarkably full picture of your hybridized system. I can also look at some of these values. My coupling is in the range of sort of single-digit MeV. The line widths that I'm talking about are one or a couple orders of magnitude larger than that. Okay, so I'm definitely in the weak coupling regime or the Purcell regime. But once I have all these parameters, I can think about measuring other quantities. Right? So I can think about, and I'll talk more about that on the next slide. My student Fawn really wanted to go for the cover of Nanoletters, and so this was on the cover of Nanoletters a few months ago. Okay, so I go back to this kind of, what does it all mean slide. So we can now measure all these quantities, okay? And so I can think about, what magic combination do I want for maximizing the Purcell effect, getting a strong coupling. One of the new frontiers in my group now is thinking about attaching multiple resonators together in arrays. And so can we tune these to then access interesting regimes where PT symmetry can be broken? What's the optimal geometry for optimizing sensing? Once we can measure these parameters, we can think about controlling them, and our spectroscopic readout allows us to measure all of these parameters. Okay,
We have a question.
Great.
Matt,
Worried I was going to get to the end. Yeah.
Hi. So when you hybridize the microresonator and the nanoparticle and then measure all these different lifetimes, does it seem like the lifetimes of like the hybridized versions seem to like split like 50-50 into like components of the individual substituents?
Right. So we can compare the hybridized quantities to good estimations of the original quantities. And they do change. But because we're not in the strong coupling regime, at least not yet, we have ideas of how to get there. Because we're not in the strong coupling regime, you wouldn't expect a sort of 50-50 split, okay? We're basically seeing the line widths, and I go back to those Fano resonances. We're basically in that phase where we can see the line shapes distort before they start splitting. And so Kevin Smith, a student in David Masiello's group, has a sort of great GUI where we can kind of turn all these knobs and go from weak coupling to strong coupling, at least in terms of simulations. This is what you would expect to see eventually. But with this particular system, we haven't gotten there yet, although I think we're getting close.
Okay.
Yeah, other questions?
We have one more question.
Hey, Randy, can you hear me?
Hey, wait.
Yeah, hi. So just help me to understand the setup.
Hey, wait, sorry, wait, you're very hard to hear. Can you speak a bit louder?
Okay. So to help me to understand, do you only have one nano rod on your turret, or you have multiple and you are just exciting one?
It's the latter. So you have multiple objects. It could be nanorods. We have other stories where it's conductive polymers. You have multiple objects on the resonator. But because we're able to locally pump one at a time, because we have this, essentially confocal beam moving around, it's diffraction limited, we can pick one at a time, right? Which is how we're able to make those plots before, where we can do spectroscopy on multiple individual nanorods that are all on the same resonator, all talking to the same whispering gallery modes. This also relates to the question I just got a minute ago of kind of how do you get to strong coupling. We can start thinking about putting more nanorods on, or other objects, quantum dots or something like that, and taking advantage of the root end scaling. Okay, but I can still do spectroscopy on each one individually, as long as they're far enough away from each other that I can resolve them, within the diffraction limit.
Right. So would the picture be that if you have enough of those nanorods around the turret, if you excite one of the nanorod, then you can transfer the energy to all the rest of the nanorod?
Yep. And so using the resonator as sort of a conduit to transfer energy between the nanorods, or again, other quantum emitters, transfer energy and potentially even entangle them. This is an area that we're definitely pushing towards. That's actually what I'll be talking about just a little bit on the next slide.
That's very cool. Thank you.
Yeah, other questions? Okay. I want to talk about kind of what's happening now. These microtoroids are very dear to my heart, but we've got a lot of mileage out of them already. we'd like to expand to other types of microdynamic photonic structures because of the different advantages and the different immersion physics that they allow. And so we have a bunch of platforms that are either almost online or coming online or just recently come online. We've been making these monolithic silicon nitride microrings. So here the taper is actually attached to the substrate, and so we don't have to worry about tapers kind of twisting in the wind, which is the biggest source of noise in our experiment. It's also the biggest source of stress amongst my graduate students. Now everything's monolithic, so it should make for a much quieter measurement. The mode volumes of these are also much smaller because the refractive index contrast is higher. We're also working with these photonic nanobeam cavities that have substantially smaller mode volumes, even than the microrings. We have some preliminary data on doing photothermal measurements with these nanobeams. We're also making these fiber-based microfabric Barreau cavities that are a little bit similar to what Saeed talked about last week. We can now fabricate these by ablating these little concave mirrors, so we can get better mode overlap between our photonic resonator and whatever object we want to hybridize with at the center. A really new area in the group is fabricating various types of topological photonic crystals, and so we're making these now with collaborators. And then I haven't spoken very much about molecules, but we're looking to take molecules and start coupling to these cavities as well, particularly at low temperature, which brings to maybe the most important thing I have to say today, which is that if you've enjoyed the particular brand of whimsy in this talk and are interested in the science, we have several new projects I'm ready to start, and so postdoc positions are available, coupling these types of, all this photonic hardware to molecules, going to low temperature, doing interesting quantum information science, doing spectroscopy. If you have low temperature experience, I would be particularly eager to make your acquaintance, so please send me an email. I see I only have a couple minutes left. And so I'm happy to answer questions, but with my couple minutes, I'll just quickly talk about one of the other frontiers in my group, which is how we take this whole operation and put it in water to actually measure chemical reaction dynamics, so dynamic systems. And so the idea is that, I'm relying on, it's a whispering gallium resonator, so I'm relying on refractive index contrast. And if I replace that air with water, right, I suddenly have much lower refractive index contrast, which means I have to make my resonators bigger in order to not to have my quality factors tank. That's undesirable. We talked about that before. But if I can put my liquid on the inside of my resonator, I can still have an air guided mode along the periphery, right? Maybe I can get the best of both worlds this way. And so we got these beautiful micro bubble resonators from Sheila McCormick's group that support a whispering gallery mode along the perimeter, but actually can be coupled to microfluidics inside of them. And so Sheila makes these things by taking two CO2 lasers and crossing them while you kind of plug the ends, and the pressure builds up even as the glass is softening, and you get this bulge of a microbubble at the center. And so I mailed one of my students to Okinawa for a couple of weeks, and Casey came back with like a briefcase full of microbubbles, and we've been doing spectroscopy ever since. Okay, I won't talk about that. The idea is we can flow liquid in and then deposit nanorods now on the inside of the resonator, and then come in with our free space beam and start mapping them, doing photothermal measurements. And they're not in solution. I shouldn't call it a solution phase measurement, but they are exposed to solution, which means we can potentially see chemical reaction dynamics. It's a little bit tricky to use these microbubbles. The mode structure is much more complicated. Depending on which mode you pick, your signal to background might be vastly different, right? Here's the same object, so you get a factor, get an order of magnitude difference, right? That's because some of the modes are much more responsive to temperature changes than others, okay? Basically, it depends. If your mode is mostly localized in the glass, you'll shift one way. If you're mostly localized in the liquid, you'll shift the other way by a much larger magnitude. And if you've got kind of 1 foot in glass and 1 foot in water, you can actually cancel out your effect. We were only finding these modes for a while, but then we figured out eventually how to find the sort of water-centered modes. We can do spectroscopy. We could also do polarization dependence to confirm that we're looking at individual objects. And then the fun part comes when you start etching in or adding an etching solution. This is a photo-induced process. It's actually plasmon enhanced. I won't have time to talk about that. But we can basically pump these individual nanorods. And at first we said, okay, cool. We're seeing them etch in real time because my signal is going down. Okay, but then we sort of measured longer and we said, oh crap, the signal's coming back. Right? That doesn't make any physical sense if we're etching them. And what we realized is that the nanorods were actually rotating as we were etching them. And so we added in this liquid crystal polarization modulator to rapidly rotate the polarization to measure out the full polarization spectrum. And that's what I'm showing here, right? And so I can keep doing this over and over again, and I can eventually watch the nanorods etch away. I can then ramp up the power, and they'll etch some more, and I can basically etch them down to almost nothing. At the same time, you can see the polarization angle has also changed. And if I put on a log plot, you can see it there, right? I'm basically rotating these things as I'm etching them. What is sort of cool and unexpected for us, but has a good precedent in the literature, we can even control the rotation by just ramping up the power, and we can actually selectively orient the nanorod in different orientations as it's etching. It's actually easier because it's etching, which hadn't been shown before. And I think I see my time is running out. Sandana hasn't yelled at me yet, which maybe is a good thing. And so I'll just put up the conclusion slides. I didn't get to talk about this additional story of looking at conductive polymers. So we're looking at materials applications as well. Thanks for your time, and I'm happy to answer more questions.
Yeah, I think we have one question from Joel.
I was going to be insulted if I went a whole talk without Joel asking a question. I don't think it's happened before.
So, Randy, I have a very simple question to ask. So, so the way you are measuring these photothermal absorption cross sections is based on temperature differences with respect to a background. My question is, since now you're going to look at chemistry and then you're presumably going to heat up, say, the solution. So I guess my question would be, what is the maximum temperatures that you can really operate under such that you can still measure a decent cross-section?
Yeah.
Background?
Yep. A great experimental question, Joel. So life definitely gets harder when you're in the microbubble. It's harder for a bunch of reasons. But one of them is because you have water, you're wicking, water is a much better thermal conductor than glass. And so you're wicking away a bunch of that thermal energy. Now, that's a bad thing. It's partially offset by the fact that the dNdt, the thermal optic coefficient in water, is larger. So you make back some of that. But we don't think of it in terms of maximum temperatures. We think of it in terms of minimum temperatures. At the limit of detection, so we're talking about atometer shift. It's hard to get to. That corresponds to thermal fluxes on the order of tens of picowatts, which translates into maximum temperature increases in the immediate vicinity of the molecule of like microkelvins. So very, very small temperature increases. Our kind of more comfortable range is, in a regime where we can measure millikelvin changes. And so, one of the tricks is, can I get to millikelvin changes from my molecule without also, pumping my background, stuff like that. And that's one of the kind of the parts we're looking to push on now, is how to minimize how to reduce the background even further. We have ideas on how to do that.
Wait, but why is it obvious that a high temperature in the surroundings doesn't really give you more like a hard background to get rid of?
Right. So if I crank up my pump laser even more, two things happen. One, you can potentially melt the nanorods, or potentially take those carbon nanotubes and basically cause them to spontaneously combust.
Yes.
We found this accidentally in the early days. We'd put our toroids in the SEM after the experiments, and there was just nothing left. It was rubble. It was literally rubble on the surface of the resonator. You might ask the question like, well, if I stay below that limit, maybe that's enough, right? But if I talk about molecules, then the limit at which I will find saturation power, and then even below that, the limit that I will find serious photodegradation is going to be orders of magnitude lower. Mm-hmm. So we'd like to operate at the largest pump power we can get to, okay, mm-hmm. without damaging the molecules, and that's what's hard to do.
I see. And a follow-up question about this is that you are talking about sensitivity, and so it has become like very fashionable to use these things called exceptional points. But then what I understand is that you need plasmonic sensors for that, whereas you have these beautiful ring resonators that have very high Qs. So I wonder if people talk about how sensitivities are enhanced near these exceptional points, and whether you
don't need plasmons to get exceptional points. So Lan Yang at WashU, amongst others, has done beautiful work getting exceptional points. In Mordechai Segev has done other work in this area. All you need is loss and gain. And in these resonators, you already have loss. It's really easy to get gain by doping in, various other, other atoms or impurities or molecules that you can then pump. And I think, and you do get enhancements in sensing at exceptional points. It is an open question whether you will get an enhancement in our particular photothermal version.
Sure.
I've spoken a bit to Lan about this as we go to more complicated systems. So it's hard to get more than 2 or 3 toroids kind of talking to each other. It's really hard. But one of the reasons we're so excited about these microrings is that it's easy to make arrays. Other groups have made arrays. And this is a space that we're looking forward to exploring as well. We have to get our fabrication chops a little bit more developed first. That's where we want to go to.
Thanks.
I think we have one more question.
Great.
Hey, Randy, this is Wei again.
Again, Wei.
So I saw that you had a reference saying that there's a microtoroid ready for made by calcium fluoride. So does that mean that this technique is also available for the infrared and molecular vibrations?
Okay, so great question. So couple of ways I can think about this. So don't be fooled by the calcium fluoride resonators that I showed you. They're macroscopic size. They're like millimeters.
Okay.
You basically make them by using a specialized diamond lathe.
Okay.
Super cool. But for getting to microresonators, I've spoken to the groups that do that, and I don't think there's a path, at least right now, for getting to microresonators made from that technique. But you can think about going to other types of materials. You can make resonators out of silicon. Okay, you can make resonators out of diamond. You might have to sacrifice some quality factor. But the key is that your probe beam can be whatever wavelength you want. It can be visible. It can be near infrared. Okay, to do kind of direct infrared absorption like you're talking about, you still need your resonator to be transparent in that region, but you only need your pumping to be mid-infrared. And honestly, the only reason we haven't done that experiment yet is that I don't have a tunable mid-infrared source in my lab. I don't think we can get to single molecule measurements that way. I have ideas about doing single molecule Raman with these toroids. I think doing single molecule photothermal in the infrared will be difficult. I don't know how to do it, but you can still do things like measure monolayers and things like that.
Got it. Thank you.
We have one more question from Juan.
Great.
Hello, Professor. I'm Juan, a grad student at UCSD. And
hello, Juan.
I have a kind of naive question. Maybe you already mentioned that you actually have multiple of these resonators. My question was if you can actually couple these resonators or how you do that to create some sort of like collective optical modes.
Yeah, so kind of build a little bit on what I mentioned to Joel. So here, I'll use this picture in the upper right. These are three-dimensional objects. And the way that Lan Yang and other groups couple them together is you basically have to fabricate them on the edge of your chip. And then you can kind of bring two chips together and use a piezo stage to control the orientation of three-dimensional space. That's already a champion experiment with two of them. And to think about networks, think about 10 of them, right? I don't see a path forward. But with these micro rings, right? In the same way that I just have my waveguide and my micro ring, just within some evanescent length, a few hundred nanometers, something like that. Depends on the wavelength, right? I couple them together, and so other groups, for many years, have made coupled ring resonators. It looks a bit like the Olympics logo, right? And you can control the coupling based on how close the resonators are together. It's in terms of fabrication, it's tricky. It requires some expertise in e-beam lithography, but plenty of people have done this. And so what we would like to be able to do is couple those, or sorry, I'm using the word couple too many times, is to add in our single molecule and single particle readout to these coupled resonator systems, or these multi-resonator systems.
Okay, thank you very much.
Mm-hmm.
I think we have a few more questions.
Great.
Jacob.
Hi, Randy, it's Jacob Krish. It's always great to see your progress with this.
Yeah.
Hi. So I had a question about what kind of time resolution you have for these measurements right now. I see my name is even misspelled here. Sorry about that. So you have this Rube Goldberg cascade right now, and with the high Q resonators, you probably have a relatively good energy resolution, which is going to cost you on your time resolution. You must have thought about how fast dynamics you'd be able to see. And I'm trying to think about whether eventually it would be possible to see different types of the thermal dissipation occurring inside of a molecular system. So for example, you have some excited state and you have a relaxation to the bottom of it, and then you have a relaxation down to the ground state. And is there any chance of seeing those different timescales of energy dissipation?
Okay, so another theorist asking me a great experimental question. So the normal limitations on the trade-offs between bandwidth and time resolution, I think don't apply here, because your spectral resolution is coming from one beam and your time resolution is coming from a different beam. There are real concerns about getting to faster time resolution. So to get to the kind of atometer ships that I showed you before, we integrate for something like 30 seconds. So it's a slow measurement. Our normal wheelhouse is 1 second lock-in time constants. And then as you tune to get a whole spectrum, you're talking about a spectrum that can be acquired in like multiple tens of seconds. And it depends how wide you're scanning. You can make that process faster, okay? But then you start running into signal noise issues. If you can pump the molecules harder and get more heat per unit time, then you can get to faster and faster. And this is sort of the a classic trade-off in time resolved experiments. You can pump harder, you risk damaging your molecule, okay, but you can get faster time resolution. Just by doing that, I think we can probably get down to milliseconds, but I don't think we can get faster than that. The resonators themselves can respond much faster, and so Barak Dayan and Frank Vollmer have published on these really interesting cavity ring up experiments to show that you can potentially get microsecond dynamics, things like that. But I think that's not valuable it's not going to help us for our photothermal readout. The way you could get to ultra fast time resolution, this has been a dream experiment of mine for a long time, is to replace this one pump beam with two pump beams. To replace that one CW pump beam with 2 pulsed pump beams, kind of an actinic pulse to start the chemistry, and then a normal pump pulse to go from, maybe from an excited state to an even higher excited state. And then, change the lag time between your actinic time and your actinic pump and your pump, and then continually reading out via CW with the coupled probe beam. So kind of, very analogous to a sort of a normal transient absorption experiment. That's how I.
No, that makes a lot of sense.
Yeah, that's how I think you can get to ultra fast time resolution. We need our sensitivity to get a little bit higher before we can make the necessary sacrifices in terms of duty cycle. And again, one of the reasons I'm so excited about these new resonators is that I think it'll help us get there.
Excellent, thank you.
I think we have a few more questions, so we should go. I think you're muted.
Oh, okay. Hello. Yes. So this is a great experiment. Very nice results. So I have a question from very beginning, because you put molecules to couple to the Stern gallery mode, right? And then you can measure the change of the refractive index to monitor the properties of the molecules. But to me, I cannot see why the non-fluorescent feature of these molecules is necessary here. So can you explain a little bit more about it?
Are you asking why is the molecule necessary, or are you asking why it's necessary for the molecule to be non-fluorescent?
Why the molecules is necessary to be non-fluorescent?
Right. Okay. So, once I send my molecule into the excited state, I have a number of ways of dissipating that energy. Typically, for most photoluminescence or single molecule fluorescence measurements, right, you want a quantum yield of as close to 1 as you can get it. You want a quantum yield of fluorescence that's close to 1. If I had a quantum yield of fluorescence that was close to 1, right, there'd be no energy or very little energy being dissipated into heat. I wouldn't see anything. Okay, my ideal molecule is molecules that have a fluorescent quantum yield of like 0 point nothing, right? I basically want 100% photothermal quantum yield, 100% thermalization, right? That just gives me more signal. So you need to be dissipating the energy thermally as opposed to radiatively. The other reason, and maybe this is the more important one, is that if your molecules or your particles are emissive, good God, don't use this technique. It's way too complicated for what you need, right? Okay. It's just super easy to do it via photoluminescence. But if you want to look at systems that are not luminescent, or you want to characterize the absorption as opposed to the emission, right? Then this is one of a small number of techniques that can actually do that.
Okay, so are you measuring the heat emitted by the molecules?
Yes. Here, wait. There's the heat.
Oh, okay. So the related question is, if you directly measure the heat emitted from the molecules, so which time resolution you can reach?
Yeah. So it's similar to Jacob's question from a few minutes ago. The ultra fast details of thermalization we are not sensitive to. So, kind of the minutia of the thermal contact between the nanorod and the glass surface doesn't matter for us. Heat energy is dumb, right? It just kind of goes everywhere, right? And so the only thing that limits us is the propagation of the heat. Let's say your molecule's over here, right? I can actually show that a little more easily. Right? Let's say your molecule's over here, right? Your whispering gallery mode is here. So you need some time for that heat to propagate over here. It's not very much time. It's, microseconds, something like that, right? But it's still, that's maybe a more fundamental limitation. If my molecule is over here, right? it's even if it doesn't take you microseconds for the heat to travel anywhere, it's still going to take you time to build up enough of a temperature change for me to see a signal.
Mm-hmm.
Does that answer your question?
Yeah. Okay. Yeah. Thanks.
Great.
I think we have one more question from Jorge.
Sandana, you've said that before. I don't think I believe you anymore. Yeah.
Jorge, go ahead. We can't hear you, Jorge.
Can you hear me?
Now we can.
Can you hear me?
Yes, we can.
Oh, hello.
Hello.
Yeah, so Jorge Campos from UCSD. So I was looking at your equation of motion, and I was wondering whether this technique could be used to test several spectral densities.
Tell me more. Sorry, can you give me a bit more context? I don't think I know. It sounds interesting, but I don't understand your question yet. I don't think
Sure. So I mean, you're able to extract these several parameters, but it looks like you're coupling to only one oscillator.
Mm-hmm.
So I was wondering whether you could think about an ensemble of oscillators and then also see the structure of the bath or something like that.
Okay, so it's all a matter of kind of what you're considering the bath. If the individual oscillators, for example, multiple whispering gallery modes, are spectrally resolved, right? Then I can see all of them. And actually, I've shown you images of that. I've shown you spectra of that already, right? That we can see how each oscillator couples to the plasmon. If that's the bath you're talking about, the kind of the photonic bath, then we can do that. If you're talking about the bath as in sort of the phonons of the resonator, or even beyond that, well, I'll start with that. If you're talking about the phonons of the resonator, there are signatures of that. So there's this kind of vibrant optomechanics community that also studies how the vibrations of the kind of mechanical vibrations of the resonator couples to the optical modes. We haven't explored that space, but there might be synergy there as well. If you're looking at more kind of high frequency oscillations like phonons in the silica, or if you're talking about solvent modes when we put it in solution, those I don't think we are sensitive to. Did that answer your question, Jorge?
Yeah, I was thinking about the latter. Thank you very much.
Yep.
And we have a question in the Q&A. So Mohammad Roy Asrori asks, what about impurity on data analysis?
Sorry, what about impurity?
On data analysis.
Impurities on data analysis. If there are impurities on the resonator, so for example, if you're putting down nanorods and you see dirt, then they'll look, as long as they're absorbing photons, they will dissipate energy. They will give us a photothermal signal. For the nanorods, one, we have relatively rigorous cleaning procedures to be used to get rid of dirt. But then even so, for example, we're looking at nanorods, it's pretty easy to tell that you have a single nanorod and not a piece of dirt because it has a transition dipole with a well-defined direction. I actually showed that here. I showed it very quickly. If you look at the polarization dependence and you see that it reaches extinction, then you have a maximum of 90 degrees off from that. You can have high confidence you're looking at a single nanorod. and hopefully a single molecule, and have it not be dirt. I should also add that when looking at polymer systems, which I didn't talk about, there's actually a lot to be learned about structural ordering that you can get from the polarization dependence.
So I think we have come to the end of the webinar. Thank you, Professor Goldsmith, for the nice talk.
My pleasure.
Before the end, let me just make one quick announcement. So I'm going to share my screen. So next week, we'll have the postdoc spotlight, which will feature Dr. Claudia Clement and Dr. Kyu Hyung Park. Thank you everyone for attending the webinar, and see you next week.